Hi everyone, Mr. O'Rourke here. Just want to walk you through how to do a few chi-squared problems. I'll give you a couple of examples today. So imagine you're using a few rats and you're interested in determining whether or not these genes for a couple of traits that you've noticed are in some way related. Maybe they're linked genes. What you see here are two rats that have two different coat colors and two different tail lengths. So the rat on the right here has a black coat and a long tail, whereas the rat on the left has a white coat and a short tail. What we're going to do is just define the short and the white versions as being recessive, as the black coat and the long tail being dominant. The genotype, obviously, for this parent then is going to be homozygous recessive for both, whereas this parent has a few options. What we're going to do is just set this parent up ahead of time as being heterozygous for both traits, having one dominant allele each. What we need to do if we're going to cross these is then put those alleles, segregate them into the respective gametes. So we'd have a genotype like this for the white and short-tailed gamete from the white and short-tailed parent, but the black coat long-tailed parent obviously has a few different setups that are possible in their gametes. We can segregate a dominant allele for coat color with a dominant allele for tail length, but we can also have the possibility of the recessive alleles segregating together. So we can have two recessive alleles, a lowercase b, lowercase l. There's also the options that we could have one dominant allele from one of the two traits and one recessive allele from one of the other two traits. So we could have an uppercase b with a lowercase l or a lowercase b with an uppercase l. These are the four possible gametes that could be produced from a heterozygous individual for both coat and tail length. What you would do when these gametes combine, we'd have our F1 genotypes. The offspring would look one of four unique ways. You could have a offspring that is heterozygous for both traits. You could have an offspring that is heterozygous for one trait but recessive for one other trait, or you can have an offspring that's heterozygous for both traits. And what you can see here then is pretty straightforward. We've got an individual like this one who's going to be carrying one dominant allele for each trait, and that would produce a black and long phenotype. And we also have an offspring that has the black allele, the dominant allele, but no dominant tail length, so this is going to be one that's black and short tail. Likewise, you can see that there's two other combinations that produce both the white and long tail and the white and short tail. Question is, what's the probability of getting these? Well, as far as our Punnett square is concerned, the ratio is pretty straightforward. It's 1 to 1 to 1 to 1. And that is to say that it's equally likely to get any of these. And if there are four possible outcomes, then the ratio for any of these, the probability is 25% or a quarter. Well, what would we expect to get if we actually did these matings? We'd expect a quarter, but what the total value or the numerical value would be would totally depend upon the size of the population. So imagine in the F1 generation we had a total sample size and total number of offsprings of 40 individuals. Well, how many would you expect then to be black and long, or black and short, or white and long, or white and short? Well, it just depends. Well, if your sample size is 40 and you know that the ratio is 1 to 1 to 1 to 1, or a quarter equally likely, you just say of those 40 individuals, a quarter are likely to be any of these. And a quarter of 40 then is just 10. So we would expect 10 black and long, we would expect 10 and short, 10 white and long, and 10 white and short, if all things were great. However, you do these experiments and sometimes the predicted outcome doesn't match the actual reality of the event. And so what if it turned out that what we observed was something along the lines of 10 to 9 to 8 to 11 in terms of the black and long, black and short, white and long, and white and short? What would you do? Would that be significant? Is there a significant difference between what we've observed and what we've expected? That's where chi-squared comes in. So let's see what we would do. And before we even do the math, let's just talk a bit about what chi-squared is and what it isn't. So the chi-squared test is pretty straightforward. It's simply something that's testing the difference between the expected and observed ratios, and it can be used in a very specific circumstance, and that is when you have types of data that's categorical, types of data that have counts to them, types of data that are frequencies. So a few examples here to make this make some sense. So imagine you were polling and trying to determine to see if there's a difference between the type of car that somebody was driving based upon their political view, or registration perhaps. If they were a Democrat or they were a Republican, what kind of car would they drive? This is a categorical type of data for two reasons. One, you're defining your category by being in the Democratic pool versus the Republican pool. Then you're also going to be defining a variable that is the category by the type of car. And in this case, the type of car could be something where it's a Chevrolet or a Ferrari or a Honda, but you can't have a Honda-Rari or a Chevronda. You have to have one or the other. There's no way to break up the type of variable that you're looking at. The same way that you may have leanings that are towards the Republican or towards the Democrat, but generally you're involved in one party or the other. You can't be a hybrid, whatever that would be between a donkey and an elephant. Anyway, the idea here is that is a great example for a chi-square test because it's not a numerical type of variable. It's a frequency. It's a count. It's a categorical type of variable. And another example would just simply, you can see, do boys and girls get sent to the principal's office equally? That may have a numerical quantity in the sense that we're looking to see how often they get sent to the principal's office, but you're either a boy or you're a girl. And you would either be going to the principal's office or you wouldn't. And that's the idea behind that question. If you were looking at the total number of times, that's not a chi-squared test. And so, again, examples of not chi-squareds, things that have numerical values that may be discrete or may be continuous. So you can be asked someone's age, and it may be, how old are these Democrats and Republicans? Well, if you're looking at the age of a Democrat or the age of a Republican, you're assigning a specific numerical quantity to that. Whereas in the original question, we were saying, if you're a Democrat or Republican, what kind of car do you drive? And you might have 15 Democrats driving Hondas. The variable here is the type of car, not the number of car. And in this case, with the age, it's the number, it's how old you are. So in the sense, this is not a good example for a chi-square test. This would be actually a great example for a t-test, which is something we're not going to talk about. So again, just come back to when you use chi-squareds, statistical tests, you're basically using a test that has variables that are in categories rather than numerical quantities. So we have categories. We have categories that are defined by the phenotypes. You are a black and long rat, or a black and short rat, or a white and long rat, or a white and short rat. And that's not a numerical quantity, although we are observing and quantifying the number of those categories that we see. When you perform a chi-square test, it's really important to not only understand that you're dealing with categorical data, but you have to start by stating a hypothesis. And with most statistical tests, we're going to start by stating the null hypothesis and trying to either prove or disprove that hypothesis based upon our statistical outcome. All a null hypothesis is simply a statement that says there is no difference. So there is no difference between what we observe and what we expect in a chi-squared test. That is, even if I see an observation of 12 black and long versus 10 that I expect, I have to determine with my chi-square test if that's statistically significant, and if I'm either going to prove my null hypothesis and accept it, or I'm going to disprove or reject my null hypothesis. If you disprove or if you reject a null hypothesis by stating that it is not true that there is no difference, that's just your classic double negative. It means that there very well might be a difference between the two sets. And that's what we're going to try to get to with their data. So let's dig into this data and see what we can do when we perform a little math. So here's your chi-squared test. And it seems a little bit bizarre at first because you have all these Greek symbols, but here's the chi-squared statistic. Kind of looks like a little curvy X with a squared symbol. This symbol is sigma, so it means we're going to be taking the sum of a bunch of individual values, and the values that we're calculating are right here. They're the observed and the expected values. So all you need to calculate, all you need to actually quantify initially are the expected values and the observed outcomes. From there, you just plug your numbers into this formula, and it's going to give you a final chi-squared statistic that we're going to use in a minute. So all the data has been done out ahead of time, but here's one example for the black and the long phenotype. We expected 10. Again, we had a total population of 40, and it was a 1-to-1 to 1-to-1 ratio, so we would have expected a quarter of that 40, or 10 individuals, to be black and long. We've observed that there were 12. How can I make this into a chi-squared statistic? Well, the first thing I need to do is write down the observed and the expected. In this case, the observed was 12, the expected was 10. I subtract the two, take the square of each of those, and divide by the number that I expected initially. So that's a nice easy number. In this case, it's just 2 squared over 10, or 4 over 10, or 0.4. The same principles apply to each of the following: the black and the short phenotypes, the white and the long phenotypes, and the white and the short phenotype as well. You add each of these up individually. You add a black and long phenotype up to get 0.4. You do it all over again for the black and short. You do it all over again for the white and long, each time performing this operation right here to get these 4 different outcomes. You then sum them up. That's the sum of each of these. That's the whole point of sigma here. You're going to add those up and you get a final value. Here is what chi-squared is equal to. And what do we do with that chi-squared value? Well, on to the next table. The chi-squared test requires you to understand a few other pieces of information. One is that what we're looking for depends upon the significance that we want to make a statement with. It gets to sort of what the statement is. The idea is that, again, with a null hypothesis, does that value, that chi-squared value, indicate that we could get that difference between the observed and the expected due completely to chance? Again, our null hypothesis was saying there's no difference. Another way of saying that this is significant is just that not only is this not different, but that the reason why we had 12 versus 10, or 9 versus 10, or 8 versus 10, that's just due to random chance. There's no significant effect going on. And so we want to know what is the chance? Is it 50% likely that that's due to chance? Is it 100% due to percent chance? Is it 1% chance that it's going to be likely due to chance alone? So you assign these different levels of probability, and you see those across this top here. These values, this would indicate 98% probability due to chance, 95% probability due to chance, and then on the other end, 1% likely due to chance, or even better, 0.1% likely due to chance. The second thing you need to understand is this idea of degrees of freedom. What degrees of freedom are used for is simply to say, how many individual categories did I have? And the number of degrees of freedom that I can use is always going to be 1 less than the number of categories I have. And if you think about it, we had 4 possible categories. It was the 4 different phenotypes. You can be black and long, black and short, white and long, and white and short. And the way that you use these critical values in this probability table is simply to say, okay, I have 4 phenotypes, I have 4 categories. The number of degrees of freedom is always going to equal the number of categories minus 1. And so in this case, I had 4 categories. I'm going to subtract 1 from that. So the number of degrees of freedom I get is 3. What that means then is that this is the column that I want to be looking at. Or rather, this is the row that I want to be looking at. And then the column that I want to be looking at just depends upon where my number fits in. Well, here's the original table right here. And we had a chi-squared value of 1. I have to figure out where this number fits in along my degrees of freedom row. And so the number 1 should fit somewhere in here, somewhere between 1.005 and 0.352. And what I can tell from that chi-squared value is that I feel like this outcome, that the difference between the observed and the expected, should happen due to chance, just random probability, somewhere between 95% and 80% of the time. You can see that the 1's a lot closer to the 80%, so you might say that I feel like the result is much more likely due to chance. It's about more than 80% likely due to chance alone. So if you're a scientist, you kind of think about, what kind of statement do I really want to make here? We sort of draw a dividing line at the 5% line. Everything to the right of the 5% line, we generally would say we reject the null hypothesis. And everything to the left of that line, we would accept the null hypothesis. That is to say, what was my null all over again? Right, it's that these genes aren't linked, that there is no relationship, there is no difference between the expected outcome. In this case, if I have a chi-squared value that's that small, I'm going to say that this is very, very likely due to chance, that any little observed differences is due to chance alone. And that's going to be something where I feel like there is no relationship between the observed and the expected. However, I might get a slightly different result. So imagine here we have a different data set. Same experiment, same rats, same 4 phenotypes, same data, different data, same math. What we have now is again, 40F1 generation, but what we observe is a little bit different than what we did before. In this case, we see a much wider variation between the expected and the observed. And so what you would expect then, if the expected and observed difference grows, we'd expect that the squared difference over the expected would also grow. And sure enough, our chi-squared value isn't 1 anymore. It's much, much larger than that. If we have a much wider variation between the expected and the observed, our chi-squared grows. And again, if we look at that table, here's your chi-squared statistic, we would have to be able to figure out, where do I plug this in? Same experiment, still 4 categories. I'm going to have 3 degrees of freedom, and 14.8 fits somewhere in here, somewhere between 0.01 and 0.001, which is to say that I think that our result, that there is no difference between the observed and the expected, well, that probably could happen due to chance between 1% of the time and 0.1% of the time. Again, anything to the right of 0.5, we tend to reject. That is to say, I disagree with that idea. I disagree with my null hypothesis that there is no difference. I think there is a difference. I think there is something going on here. And very likely there is a significant difference between what I observed and what I expected. That's the idea behind chi-squared. It's a very useful tool. Feel free to contact me if you have any questions, and I hope that helped.